All right, today we are learning how to balance nuclear decay equations. And so let's talk about how nuclear reactions differ from chemical reactions. Because so far this semester, and even last semester in Chem 1, we haven't dealt with any nuclear reactions yet. We've only dealt with chemical reactions. So let's look at some of the major differences between nuclear and chemical reactions. So in a chemical reaction, we never change identity, right? You start out with carbon and hydrogen and oxygen, you end up with carbon and hydrogen and oxygen, right? No change in identity. Whereas in a nuclear reaction, you are changing identity. Remember, if you change the number of protons, you change the element. That's one of the first things we learned when we first began studying chemistry, is that the identity of an element is defined by the number of protons. Well, in nuclear reactions, the number of protons is changing, and thus you're converting into new elements. In chemical reactions, electrons and orbitals are primarily what's happening. What's taking place is electrons and orbitals are involved, bonds are breaking, but nuclear particles, so in other words, particles in the nucleus, the protons and neutrons, they're not participating in any way. However, in a nuclear reaction, electrons aren't doing really much in orbitals, they're just kind of hanging out. But the protons and neutrons, they are the ones participating. We talk about changes in energy in chemical reactions, and yes, things are exothermic. You know, you feel your beaker get hot, right? But it's a drop in the bucket compared to the energy changes in nuclear reactions, okay? You can be in the room and have a chemical equation, a chemical change happening, and it's not going to kill you. But if a nuclear change is occurring in the room, the energy could be enough to take you out, right? So there's a big difference in the energy in terms of a chemical reaction versus a nuclear. And then what is the primary influence on rate? Think back to kinetics, right? Temperature, concentration, catalyst, and then the identity of the compound. Whereas here, the rates are primarily dependent on the number of nuclei, how many nuclei are undergoing the reaction. And catalysts and all that stuff, they don't really have any influence. So we need to make sure that we take some time and look at how we represent protons, neutrons, and electrons in nuclear chemistry. All right, we represent an electron as 0, -1 e. We represent a proton as 1, 1 p, and we represent a neutron as 1, 0 n. Okay, and this is in the notes online, so you can download it if you miss it in your notes right now. All right, this is how we represent protons, neutrons, and electrons in nuclear chemistry. And so many nuclides are unstable, which means they spontaneously emit radiation. That's the definition we're going with for unstable. And we call that process radioactive decay. And then during that decay, we're going to emit radiation. We're very likely going to change into a different element as well. Now, there are several nuclear reactions that we're going to learn, and this is kind of dependent on the type of reaction we're looking at, right? Because there are a couple of cases where it's not going to change it to a different element. So I will show you an example today where you're not going to see that, but the majority of the time it's going to change it to a different element. Now, the law of conservation of mass still applies, okay? The total mass of the reactants is still going to equal the total mass of the products. Now, if you think back to the very beginning of the school year in Chem 1, when we learned how to write nuclear symbols, right? A nuclear symbol is the mass number over the atomic number, and then the symbol. Okay, so when we're doing these kinds of reactions and our study of nuclear chemistry, law of conservation of mass is still going to apply. Okay, the total mass number of the reactants is going to equal each other, and the total atomic number is going to equal each other. Okay, so we need to make sure that we're writing our decay equations to follow the law of conservation of mass. So mass number on the left needs to equal mass number on the right, and atomic number on the left needs to equal atomic number total on the right. Okay, so just something to keep in mind as we start balancing these nuclear reactions today. And so make a note to yourself that you're going to need to learn these 5 types of particles and the types of nuclear reactions. That's just something you have to commit to memory. Make yourself some flashcards, however you want to do it. But this is something you have to have committed to memory, okay, in order to be able to do this. And so I'm just going to make a little cheat sheet off to the side here for us to use today while we're going through these problems. Okay, proton is 1, 1 hydrogen, which is the same thing as 1, 1 P. Neutron is 1, 0 N. Electron is 0, negative 1 E, which is the same thing as 0, negative 1 B. We'll talk about what that B stands for. That's the Greek letter beta. Okay, positron is 0 plus 1 E, which is the same thing as 0 plus 1 B. And alpha particle is 4, 2 alpha, which is the same thing as a helium atom. Okay, you need to commit this to memory. Okay, we're going to make ourselves a little cheat sheet because we're going to be balancing equations today, and we're going to be referring back to this. Okay, so this is the exact same stuff that's in the notes. Make yourself a note. You need to memorize this. Okay, you got to know this stuff. So the modes of decay. Let's go through each one. So alpha decay is when you lose an alpha particle. Okay, it's a very common form of decay if you've got a heavy isotope. So for instance, here's what I mean by balancing the equation. Notice the total mass number, the total atomic number is 88. Total on this side is 88. Right? That's the total atomic number is 88. Total atomic number is 88. Total mass number, 226. Total mass number is 226. So for alpha decay, you would take your nuclide that you're beginning with, and you would then write alpha particle, and then you'd figure out what element needs to be right here. Right, so 226 minus 4, that gives me 222. And 88 minus 2, that gives me 86. I look up element number 86 in my periodic table, and that's radon. For beta decay, we're losing a beta particle. Okay, so again, we're following the law of conservation of mass. If I say, all right, here's the nuclide that I begin with, and it's undergoing beta decay, what does that mean? All right, so we take the mass number that we're beginning with, and we know that a negative 1 is going to be involved, right? All right, so to obey the law of conservation of mass, that means this needs to be up 1. Element number 29 is copper. And this is 0, so that number stays the same. Again, so we're using the law of conservation of mass. So that's a beta particle. So if you're keeping track on your notes, right, this would be beta decay. Okay, positron emission is when we lose a positron. So again, if I say, all right, here's the element you begin with, write a positron emission for it, you would say, okay, law of conservation of mass. If this is 6 and I know positron is this, what does this need to be so that it adds up to 6? It must be a 5. I know that this number is 0, so that means that this one doesn't change. Look up element number 5, and it's boron. And electron capture is the only one where a reactant is involved. Right? So all these other ones are showing our radiation as a product. Here it's being a reactant. Right? So we're capturing an electron. And so again, following the law of conservation of mass, if this is the nuclide we begin with, -1, that means it's going to go down by 1. 0 means it's going to stay the same. So again, if you're keeping track on your notes of which ones go with which, this one goes with positron emission, and which one did we just talk about? Electron capture. That one would go with there we go. And then this one goes with alpha decay. And then there's one that we left off the list, and I'm going to have to add it to my list because we're just going to see it right here. Just realized that I left gamma particle off my list. Gamma emission is when you get a gamma particle. So here's the only one where the identity isn't going to change because it's 0, 0, and that's a gamma. It's the lowercase Greek letter gamma. Okay, it's not a Y. So it's 0, 0. So notice the identity doesn't change. This is the only nuclear reaction we're talking about where the identity doesn't change. You're just emitting a high energy photon. Remember, photon is energy. So I left gamma particle off my list a few minutes ago. Zero, zero, gamma. Okay, and that goes with all right. So now what we're going to do is we're just going to go through examples. This is a figure from your textbook, basically just showing the same thing, right? It's showing what's changing the atomic and the mass number, right? But I mean, you can read that for yourself. So let's do this example together. I'm just going to leave the screen. Write a balanced equation for the nuclear reaction that occurs when thorium-232 undergoes alpha decay. All right, so the first thing you need is your handy-dandy periodic table. And I told you it was thorium-232. So that's TH, mass number is 232, and thorium is element number 90. All right, so this is undergoing alpha decay. So I look at my little cheat sheet and say to myself, okay, alpha decay is emitting an alpha particle. All right, so that means I'm going to be producing something plus 4 to alpha. So now I've just got to obey the law of conservation of mass, right? 90 is the total on this side, so that means that 90 needs to be the total on this side. So I've already got 2, so that means that I need to have 88 as the atomic number. And I've got 232 on this side and 4 on this side, right? So I subtract 231, 230, 29, 28, right? So that's 228. And now I just need to look up what element number 88 is. Element number 88 is radium. Makes sense, right? Obeying the law of conservation of mass. This is what I'm saying you have to learn these guys, okay? Because otherwise you won't know what goes here to be able to fill in the blank here. Here's another one. Let's just do for practice, and then I'm going to give you some to try. So this is zirconium-86. So zirconium, mass number is 86. Zirconium is element number 40. Now this is undergoing electron capture. So that means that it's a reactant. And so we need to figure out what we're getting. Electron capture means that you've got an electron being captured, hence the name electron capture. Right, so that means zirconium plus 0, -1 E, and then we need to figure out the product. All right, so 40 plus -1, that gives me 39, right? So that means that the mass number, I mean the atomic number on this side needs to be 39. 86 plus 0 is 86. So now I just look up element number 39, which is yttrium. All right, so here are some that I want you to try. I'm going to pause the recording, give you a few minutes to try these here in class. So 3 to try. I'll give you a few minutes to work on these, and then we'll go over them. All right, let's go over these. So we've got some problems that we're going to go over. I lost my remote. Oh well. So let's go through them individually. That's kind of in a bad spot, isn't it? Move the question over this way a little. There we go. Oh, still need to move it over just a touch. Because we're going to be using our cheat sheet today. All right. We've got uranium-238, so we're going to need our periodic table. Uranium-238, so 238, and the atomic number of uranium is 92. And it's undergoing alpha decay, so that means we're going to be producing an alpha particle, 4, 2, alpha. And then we just need to figure out what else. Okay? Alpha decay means we're producing an alpha particle, and again, we've got to follow the law of conservation of mass. So the top needs to add up to 238. So that means on this side, we need to have 234, right? Because 234 plus 4 is 238. And on the bottom, we need to have 90. Because 90 plus 2 is 92, and 92 over here. Now we look up element number 90, and that's thorium. Feeling good about this one? So these aren't difficult problems, right? You just have to make sure that you're following the law of conservation of mass. All right, let's do the next one. I need to move my question over like I did for the last one. All right, so this one's electron capture. So you just need to know which of these to go with. We've got palladium-106. So atomic number of palladium is 46. So 46, and we're told this is palladium-106, so that's its mass number. All right, it's undergoing electron capture, so that means that it is grabbing an electron. So 0 minus 1 E. Okay, we got to follow the law of conservation of mass. Right, 46 plus -1. So what does that mean? 46, -1. So this needs to be 45. Right? Because 46 minus 1 will give me 45. 45 over here. And 106. So element number 45 is rhodium. So all we're doing is just applying the law of conservation of mass. Electron capture. All right, on this one. All right. Let's move this over. This is actinium-223. Actinium's down here, it's number 89. And this is 223, is the mass number, actinium. And so this is gamma emission. right? So that's 0, 0, gamma. And since these are both zeros, the identity isn't changing. So that one's easy, right? Because 0 plus 223 is 223. 0 plus 89 is 89. All right. Got a couple more for you to do here. So try these two. I'll pause the recording and then we'll go over them. We've got a second type of problem we're going to do as well. All right, let's go over these. We're doing more nuclear decay equations, which require us to know our alpha particles and our modes of decay, and our nuclides and our modes of decay. So now we're doing beta decay of Rutherfordium-264. So Rutherfordium-264, where's Rutherfordium's mass number? And atomic number. Rutherfordium, where are you? There we go. It's element number 104. Didn't know that one off the top of my head. Don't do a lot with Rutherfordium. So 104, and this is 264 is the mass number. Now this is beta decay. Beta decay means this is a product. So we're going to produce a beta particle, 0 minus 1 beta plus. Now we need to figure it out. All right. For the bottom number to equal 104, got a negative 1 here, so this needs to be 105, right? Because 105 minus 1 gives me 104. And the top number is 0, so this is 264. So the mass number doesn't change, just the atomic number. So element number 105 is dB. And then the next one, positron emission of Seborgium-265. So Seborgium's element number 106, and its mass number is 265, Sg. Positron emission, positron looks like this. Okay, so we produce 0 plus 1 beta, and we need to follow the law of conservation of mass. If this is plus 1, this one needs to be 105, right? Because 105 plus 1 is 106. This is 0, so the mass number doesn't change, so 265. And element number 105, same as last time. So that's the first type of problem. You used what kind of decay it was to figure out the new nuclide. Let's go the other direction. And let's look at an example where I give you a reaction and ask you to solve for X. So it's just literally working the other way around. You're figuring out what kind of decay took place. So I guess I can get this down. If we've got I'm going to write it down here, 212, 84, PO, 208, 82, PB plus X. Okay, so in other words, the problem's asking us what kind of reaction took place. Right? We just have to follow the law of conservation of mass. 212 to 208, the difference there is 4. And the difference between here is 2. Well, there's only one that's got that scenario. So X equals, and so this must have been alpha decay. Right? So you're just using the law of conservation of mass to solve for X. So I think I've got a couple on here for you to try. Yes, I do. Move it over. Move the whole thing over. There we go. All right, solve for x. I'll pause the recording. All right, let's solve for x here. So again, all we're doing is applying the law of conservation of mass. Top number didn't change, so that means that the change in mass number is 0. And this went up by 1. So what can the bottom number only be for this side to equal this side? It's got to be -1, right? Because 95 minus 1 gives me 94. So 0, -1, what does that correspond to? That would be this one, beta decay. So that's what x equals. This must have been beta decay. And one more to try. Solve for x here. And identify the type of nuclear decay that occurs here. All right, let's try this one. Again, we're following the law of conservation of mass. If we want both sides to equal each other, this goes up by 1, so that means that the bottom number needs to be -1. Top number doesn't change, so it's the same as the previous one, right? This is also beta decay. Because 100 plus -1 gives me 99. 253 plus 0 gives me 253. All right, so that's where we're going to stop in terms of writing and balancing nuclear decay equations. And the next time we meet, we will be discussing how to do the kinetics of nuclear decay. So we're going to be reviewing our kinetics. Yay! And that's where we're going to stop.